Hello everybody and welcome to our video on integration by parts. So we're going to start by taking a look at a theorem, and that's the integration by parts theorem. And then we're just going to start evaluating some integrals with that. So the theorem for integration by parts is a relatively simple statement. It says if f of x and g of x are both differentiable, then the integral of f of x times g prime of x dx is equal to f of x times g of x minus the integral of g of x times f prime of x dx. So what integration by parts allows us to do is take an integral that has a product of two functions that we can't really work with directly and rewrite it in terms of the integral of f's derivative times g's antiderivative, or g prime's antiderivative, I should say. So, in other words, we can rewrite the integral in a way that might have functions easier to work with. So, alternatively, we often write this integration by parts formula as u equals f of x, v equals g of x, and so then du is written, or f prime of x dx is written as du, and g prime of x dx is written as dv. And so that allows us to express the rule in an easier to memorize form. So it's not as detailed, but it is easier to memorize. The integral of u dv equals uv minus the integral of v du. Now, the proof for integration by parts is a proof that I really like because it's actually quite simple and straightforward. So essentially, integration by parts is just based off of the product rule for derivatives. So we start by writing out the product rule for derivatives, d dx of f times g. So the derivative of f times g is equal to df dx times g plus f times dg dx. So we integrate both sides of this equation, and we get the integral of the derivative of f times g with respect to x equals the integral of df dx times g plus the integral of f times dg dx. So now we've integrated both sides, and what do we see? Well, since here we're integrating the derivative of f times g, what do we get? We get just f times g, right? The antiderivative of the derivative is the function, so we get f times g. Now there is a constant involved here, but that constant is hidden in these integrals on the right side of this equation, so we don't have to worry too much about that until we've actually evaluated an integral. Okay, so where were we? So the left side of that equation, we had the antiderivative of the derivative of f and g, so we just get f times g. And then the last step here is just to subtract one of the terms from this side. So I subtract the g of x times f prime of x integral from the left side, and what do we get? The integral of f times g prime dx equals fg minus the integral of g times f prime dx. Okay, so a pretty straightforward proof. There's only really three big steps, and when you're trying to learn proofs, by the way, little advice is to start by just getting a bulletproof list, or a bullet point list of items that are the main things that you do in the proof. So in this case, for example, I would summarize this as write the product rule, integrate both sides, and rearrange. And so start by working on memorizing just the key steps, this descriptive property. What do? We write the product rule, we integrate both sides, and we rearrange, and then try to actually write out the proof yourself with only that as your set of guidelines. This is something that's pretty easy to memorize. This little bullet point list is very easy to memorize. Trying to memorize an entire proof, not so easy. So you want to just have key steps that you memorize, and then you just work from there to actually write out the proof. Okay, so with that being said, let's go ahead and apply this. So when you are first starting out doing integration by parts, one of the things I would suggest is every time you do a problem, write down the formula. In particular, the version in terms of u and v. That's going to make this a lot quicker for you to memorize. So the integral of u dv is uv minus the integral of v du. Okay, so we wrote that down. If we do that every time we do a problem, that's just 5-10 seconds added to the problem. By the time you're done doing your homework on the topic, you'll have that formula really burned in good. Okay, so now we're going to actually start working out this problem, and the tricky part is identifying what part of the integral you should be calling u and what part you should be calling dv. Right, so that's the integral we have here, u dv, and the trick is to figure out what's what. So I always want my students off to the side to write out their u and their dv, and consequently their du and their v terms. So that's going to make things a lot clearer, easier for your grader to read and understand, and it's going to make it a lot easier to give partial credit when a student makes a mistake. Because if we can see exactly what you identified as u and dv in a very organized way, then we can see where you went wrong if you do make any mistakes later in the problem. Okay, so here's the general principle. When I rewrite this formula, I'm going from u to du, so I'm taking a derivative of one of the terms, and I'm going from dv to v, so I'm taking an antiderivative for the other term. So I want to pick terms where taking the derivative of the one thing makes it simpler, and taking the antiderivative of the other thing at least doesn't make it worse. That's the goal. So I look at this and I think about, okay, x. Well, the derivative of x is 1. So that makes things pretty simple. So that's what I'm going to pick for my u. So I'm going to say if u is x, and then I'm going to say, okay, choose dv then to be what's left. E to the x dx. Don't forget the dx part. Okay, so these are the things that I'm choosing. I'm identifying these from the integral expression. And now I have to compute what's du and what's v. Well, du is simple. The derivative of x is 1, so du is 1 times dx, right? Now remember, this is like a little bit of a shortcut. We're saying du dx is 1, and then I'm multiplying dx across, so du is just dx. But we usually will skip straight to having the dx on the right side here, because what we're trying to replace is that dx expression. And now we find the antiderivative for v. No, or for dv. So dv is e to the x dx. So again, this is similar to saying dv dx is e to the x. So what's v? The antiderivative. So v is e to the x. So what I boxed in here, that's what I chose for u and dv, and what I circled here is what I computed based on that u and dv. All right, so now we just apply it. So we take our integral, so I'm going to just use I to be my integral here. So my integral x e to the x dx is equal to what? Well, now I can rewrite this as uv, so I look over here, u is x, times v is e to the x, minus the integral of v, that's e to the x, du, and du is dx. Okay. And now the next step is pretty straightforward, because we know the antiderivative for e to the x is just e to the x. And now that all of my integral symbols are gone, we've got to put our constant here. So keep in mind, whenever you find an antiderivative, there's a plus c, but we don't really need to start writing it until after our last integral expression has disappeared. Then we can tack our plus c on at the end for these problems. Okay, so integration by parts for definite integrals. Statement's basically the same thing, except it says if we're integrating from a to b, once we apply the integration by parts formula, we evaluate the whole expression from a to b. So it works the same exact way we deal with any other definite integrals. So in this case, we've got the same integral here, x e to the x dx. So I'm not going to redo all the work. I'm just going to say, hey, I integrated this whole thing. I applied my formula. I integrated it. I got this result, x e to the x minus e to the x plus c. We don't have to worry about the constant for a definite integral. So we can just write x e to the x minus e to the x. I have a great memory, but it's short. That's a very silly joke. Okay, so we're evaluating from 1 to 2, so we just plug in our upper bound first. It's 2e squared minus e squared. Plug in the lower bound, it's 1e to the first minus e to the first. So this gives me 2e squared minus e squared is just 1e squared. And then e minus e is 0, so that's it, e squared. Okay, so now let's try another one. Now we'd already done the work here. If you were doing a definite integral from the start and you hadn't yet found your antiderivative, you of course would have to do this work here, show the actual application of the formula. But we're saving a little time here. Now for example 3, we've got the integral of 2x minus 1 times sine of pi x dx. So what can we do here? Well, again, my thought process is I'm trying to apply this formula, the integral of u dv equals uv minus the integral of v du. And I want whatever I pick for u, when I take its derivative, I would like to get something simpler if I can. That won't always work out perfectly. We'll see examples of that later. But I want something simpler. So I've got a product here, u times some dv. So what do I pick for u? What do I pick for dv? Well, when I look at 2x minus 1, I think, hey, 2x minus 1, take the derivative of that, it's just 2. So that seems like a really good choice for u. U is 2x minus 1. So then du is just 2 dx. Again, du dx is 2, so I multiply the dx across. All right, so I picked u as 2x minus 1, and I'm picking dv to be everything else that's left. So dv here is sine of pi x dx. Now in the future, I'm gonna start skipping over this little antiderivative step here, but we'll do this off to the side just to illustrate. So I need the antiderivative of sine of pi x dx. And so I have to do a substitution here, because this isn't just sine of x, it's sine of a constant times x. So I'll let w be pi x, so dw is pi dx. So dw over pi is dx. So I can rewrite this as the integral of sine of w dw over pi. And of course I can pull the 1 over pi in front of the integral. And so that's 1 over pi. And the antiderivative of sine of w is negative cosine of w plus a constant. And altogether this becomes negative cosine of pi x over pi plus c. So this is my v. So we'll just write that up here now. V is negative cosine of pi x over pi. So just to touch on this a little bit more, whenever I'm making a substitution where the only thing inside is a constant times x, I know that I'm always going to basically get the normal antiderivative of that thing divided by that constant, right? In this case, the constant is pi, so I get negative cosine of pi x divided by pi. So whenever I have these kinds of substitutions in the future where it's just times a constant, I am going to skip that step just to save some time here. Just try to keep that in the back of your mind. Okay, back to the integration by parts. I picked u as 2x minus 1 and dv as sine of pi x dx. And I computed that du therefore is 2 dx and v is negative cosine of pi x over pi. Now I can apply my integration by parts. Again, my integral is I, so we write I equals uv. It's 2x minus 1 times negative cosine of pi x over pi minus the integral of v du. Okay, v, that's negative cosine of pi x over pi. And du is 2 dx. I'll take this negative here, and I'll I'll distribute it, I should say. So this is really like negative 1 times cosine of pi x over pi. So I can take that negative 1 and distribute it here. And if I do that, the negative 1 that was here becomes positive 1, and the 2x becomes negative 2x. So I just am writing this a little bit cleaner. 1 minus 2x times cosine of pi x all over pi. And now here we've got two negatives, so those cancel. And we've also got the constant 2 over pi. So this becomes plus 2 over pi times the integral of cosine of pi x dx. And so now exactly the situation I said was going to come up again, just did. We've got an integral of cosine of pi x. So I technically need to do a substitution here. But again, it's a constant multiple, so I'm just going to skip that step. So the antiderivative of cosine is sine, so this will be sine of pi x, and I'm going to end up dividing by that constant, which was pi. And now that all of our antiderivatives are done, we'll just tack on our constant of integration at the end here. Now, that answer would have been totally fine, but I'll write this in a slightly simplified way. So I've got 2 over pi, and then in the denominator, this is being multiplied by pi again. So I'll write this as 2 over pi squared times sine of pi x plus c. Okay, all done with that one. Let's move on. Okay, so now we've got another definite integral here. And again, my same thought process reigns supreme. First, I want to write out my formula. U dv is uv minus the integral of v du. And I'm thinking, hey, what thing if I pick it to be u and I take the derivative, I end up hopefully with something simpler. And I look at t squared and I think, well, the derivative of t squared is 2t. And linear functions seem to be a little simpler than quadratic functions. So let's see what happens when we make that choice for u and v. So that means u is t squared. And if u is t squared, then e to the t dt has to be my dv. And so du is 2t dt. And v, well, the antiderivative of e to the t is just e to the t. So v is e to the t. Now, I take my integral I here. And this thing is going to be equal to, well, I do my integration by parts formula, uv t squared e to the t minus the integral of v du. And of course, we're multiplying here, v du, and I can multiply in any order. So just because it's a little nicer, I'm going to put the 2t in front and the e to the t after. But again, it's still v times du here. I just changed the order of multiplication, which is fine. And this whole thing is going to get evaluated from 0 to 1. Now I do need to integrate further here, but I'm going to simplify a little bit first. Actually, let me move this around. I want that space off to the side. T squared e to the t minus, and I'm going to pull that constant 2 out in front. So minus 2 times the integral of t e to the t dt. And again, we're still going to evaluate from 0 to 1. But now we've got this integral of t e to the t dt. Now, even though we basically already did this antiderivative before, I'm going to go ahead and do it again just to reinforce it a little extra. So I need to do another integration by parts here, and that happens pretty frequently, right? You do one integration by parts, you might have to repeat it again if you've still got the same type of expression around. And so this is a very standard kind of example for that situation. So here, I'm going to, just for clarity, call this u2. So u2, I'm going to pick to be t, because again, hey, when I take the derivative of t, it becomes something easier. It becomes 1. So I think, well, that simplifies this expression a bit. I get 1 dt. And then my dv2, well, if I picked u2 was t, then dv2 has to be what's left over, the e to the t dt. So v2 is e to the t. So very similar integration by parts here, our second time around. Now, of course, imagine if I'd started with a third degree polynomial, just doing integration by parts twice would not have been enough. You would have had to do it again, and higher degree polynomials require more repetitions of the integration by parts. Okay, so here we're just taking this integral t e to the t. Again, we're applying uv minus the integral v du. So we get t e to the t minus the integral of e to the t dt. All right, that's just the integration by parts going from here to here. And we still need to evaluate this whole thing from 0 to 1. You really want to make sure you keep putting those marks every time. That's very common for students to stop writing your evaluation marks, and then you get to the end and you forget, oh wait, I'm supposed to evaluate this thing. And so you just leave it as a function when you should be plugging in those numbers at the end and getting a value at the end. Okay, but we do have one more integral to complete. So we get t squared e to the t minus, I distribute the 2 here, 2t e to the t, and this is a negative 2 times this negative, so that's going to become a positive 2, and the antiderivative for e to the t is just e to the t. Now I could go ahead and plug in the 0 and 1 now, but sometimes it's a little bit easier to compute these things if you actually do a little factoring or simplifying first. And I notice that I can factor out e to the t here. And it's not going to make a big difference, but it can make evaluating at these numbers slightly easier. Okay, so now I need to evaluate at 1. So I get e to the first power times 1 minus 2 plus 2, which is just 1, minus e to the 0 times, and now we plug in 0, 0 minus 0 plus 2, which is 2. E to the first times 1 is just e. E to the 0 power is 1, so this is minus 2. 1 times 2. Okay, that's it for that one. Okay, so now we get to a problem that is quite a bit trickier. And that's the integral of e to the x cosine of x dx. And it's a little bit trickier because the thought process we've been using so far kind of falls apart. So in the previous problems, we kept saying, okay, well, what do I pick for u? I pick the thing that when I take that derivative, it becomes easier. In this case, there's no such thing, right? If I take the derivative of e to the x, I just get e to the x. And if I take the derivative of cosine of x, I get negative sine of x. So both of these, they stay about the same complexity, if that makes any sense. So if they stay about the same complexity, then how do I know which one to pick, right? I've got these product of two things. It looks like maybe I should use integration by parts. Well, in this case, it actually doesn't matter which one you pick. You can pick either e to the x or cosine of x for u, and we're going to be able to work it through. But I'm going to go ahead and pick the trigonometric function. I'm going to pick cosine for my u. And you'll see why I picked cosine for my u in just a little bit later. Okay, so cosine of x is u. So I should write this a little differently. I should underline this. Cosine of x is my u, and my dv is going to be e to the x dx. So then du is going to be negative sine of x, and v is going to be e to the x. And again, I'm going to write out my formula, u dv equals uv minus the integral of v du. And now we're going to take my integral, which is I, right? I'm calling this integral I. And I'm saying, okay, I can rewrite this with integration by parts as u, which is cosine of x, times v, that's e to the x, minus the integral of v du, e to the x times negative sine of x dx. Oh, I forgot to write my dx there. Shame on me. dx. There we go. Now, I'm going to simplify this a little bit. Negative times a negative is a positive. This becomes plus the integral of e to the x sine of x dx. Now, a natural first reaction to this problem is to go, wait, that was useless. Because this looks no better than the integral for e to the x cosine of x dx. I just have e to the x sine of x dx, which I don't know how to do either. That's okay. That's a pretty normal reaction, because what we're going to do is a pretty clever trick. But what we're going to do is we're going to apply integration by parts to e to the x sine of x dx again. And again, this is another one of those things where by the time you see the end of the problem, you'll see why we chose to take this approach. So u2 is going to be, and the one key thing about this type of problem when you have these combinations of e to the x and sine or cosine is make sure you make the same type of choice for u both times. So I chose u to be my trig function before. I'm going to choose u to be my trig function again the second time I apply integration by parts. If you don't, it will end up doing nothing. You'll just spin your wheels and won't get any results. So if I pick my second u to be sine of x, then du will be cosine of x dx. And my second dv has to be then e to the x dx. So my second v is e to the x. And so now we're going to write this expression e to the x sine of x. We're going to rewrite it using integration by parts again. So we get u v minus the integral of v du. So again, this. We applied integration by parts, got this. Now, This is the key. What we have to recognize in this type of problem is that we just got the same exact integral that we started with. So now I can actually treat this integral like a variable and solve it algebraically. Remember, this whole expression is equal to I. I is equal to the whole thing. So I can rewrite what I've gotten here as an equation of I equals cosine of x e to the x plus sine of x e to the x minus I. That's the key, because I is that integral. And now I can just solve this algebraically like I would for any other variable. I add I to each side. So I get 2I equals cosine of x e to the x plus sine of x e to the x. And one little thing is that now that we no longer have an integral on the right side of the equation, we've got to put that constant of integration. So remember, whenever there's an integral, that constant is there, it's just hidden in that integral notation. Once we move all of our integral signs across the equation, that's the time we got to make sure we put our plus c. Now I can divide by 2, so I get I equals cosine of x e to the x plus sine of x e to the x over 2 plus c over 2. But I'm never going to write this c over 2 here, because if I don't know what the constant is and I divide it by 2, it's still a constant that I don't know what it is. So typically, you're always going to write your final answer as just a single unknown constant. You don't need to write any multiples or dividends of a constant. I'll just say call it k, change the name of it. Now this is a perfectly fine way to write this answer. I will just point out that oftentimes you will see these answers written as, say, e to the x times cosine of x plus sine of x over 2. So very common to just see any common terms factored out. Okay, that's it for that one. Just to summarize though, again, we started out by applying integration by parts, did a little simplifying, and applied it again, and realized that we had written the original integral in terms of an expression minus the original integral again. And so we turned this into an algebraic equation, I equals cosine of x e to the x plus sine of x e to the x minus I, and solved it algebraically. And so we got, again, I equals e to the x times cosine of x plus sine of x all over 2 plus a constant. All right, so those are somewhat tricky problems. The following one is also kind of tricky, but it's not that bad once we kind of figure out how to go with it. So the tricky part with this one is we're used to, in integration by parts, seeing two functions, right? An f and a g prime. But what we have to remember is there's always a multiple of 1 here. So we only see one function here, but there's also the function 1, right? So in this case, it's actually pretty straightforward because we only have one possible choice for u and dv. U has to be the function arctan of 2x. We know the derivative for arctan of x. Sorry, I said arctan of 2x, arctan of 2t. We know the derivative for arctangent. And of course, we've got 2t in here, so we have to apply a chain rule. So applying the chain rule, I get 1 over 1 plus 2t squared times the derivative of 2t, which is 2 dt. And dv has to be just our 1 dt, and so v is going to just be t. The antiderivative for 1 is t, so that's that. Again, it's always good to when you are first learning this, write that integration by parts formula explicitly every time, just to help memorize it. Okay, so now my integral I is, all right, we apply integration by parts, uv arctan of 2t times t minus the integral of v du. That's t times 2 over 1 plus, and I'm going to, instead of writing 2t squared, I'm going to write this as 2t times 2t is 4t squared. 4 times t squared, right? So this is 2t all squared. Now I'm squaring it and making 2 squared is 4, t squared is t squared, and dt. And this thing needs to be evaluated from 0 to 1. Now when I look at this, I see a substitution here, but it's not a simple constant multiple substitution. So I'm going to set this to be my w. W is 1 plus 4t squared. So dw is 8t dt. And here I've got a t and a dt. So I'll just isolate the t dt. Get dw over 8 equals t dt. So this becomes the antiderivative of, let's see, t dt was dw over 8. So I'll put the dw over 8 at the end. And then up top I've still got a 2, and in the bottom I've got w. Now one thing that I want to see students do, whenever you have inside your integral bounds, you start having two different variables, one for this expression and one for a separate integral, right? We've got two different things here. I want you to mark your variable for your evaluation bounds explicitly, because now it's not just written in terms of t, so we want to make sure it's clear that these evaluation bounds are from t equals 0 to t equals 1, not w. So you've got to switch back to t before you evaluate there. Okay, so this is arctangent of 2t times t minus 2 over 8 is 1/4. And then we've got all that's left is the integral of 1 over w dw after I factor the 1/4 out. So what do I get? I get the ln of the absolute value of w. Again, evaluated from t equals 0 to t equals 1. And now I plug in my value for w back in. Now notice this is the absolute value of w, but w here is 1 plus 4t squared, and since the variable is squared here, and all these terms are positive, it can only be positive, so I don't need to write the absolute value anymore. And now since I've changed everything back to just the variable t, I can go back to just writing from 0 to 1 without specifying. Okay, now we got to plug in our bounds. So we plug in 1. That gives us arctangent of 2 times 1 minus 1/4, the natural log of 1 plus 4, which is 5, minus arctan of 0 times 0 minus 1/4 ln of 1. And we know ln of 1 is 0. Arctan of 0 is also 0, but it's also being multiplied by 0. So regardless, this whole second expression is going to be 0. And so we just get left with arctangent of 2 minus ln of 5 over 4. All right, that's it for that one. So we have sort of a general guide here. You can usually use the acronym LIAT. So logarithmic, inverse trig, algebraic, trigonometric, and exponential to determine which term to differentiate when using integration by parts. You differentiate the term that's furthest to the left in LIAT. In other words, which thing do you pick for u? You pick whatever type of expression is furthest to the left in LIAT. So we can see this in the previous examples. I'll go back. So LIAT, well, what do we got? Logs, nope. Inverse trigs, nope. Algebraic, yeah, x is an algebraic function, so we picked x for u. Then we look at this example 3. Again, logs, there's no logs. Inverse trig functions, not there. Algebraic, yeah, 2x minus 1 is an algebraic expression. I picked that for u. Okay, here we've got t squared. Again, t squared is algebraic. A lot of times, algebraic expressions will come up. So I picked that for you. And here, log expressions, no. Inverse trig, no. Algebraic, no. Trig, oh, I picked trig for you. So even though I mentioned before that in this particular problem, I could have picked either e to the x or cosine of x for you, I picked cosine of x just to be consistent with the LIAT method. And here, so we've got logs. No, there's no logs. Inverse trig. Oh yeah, arctangent. That's an inverse trig function, so I picked that for you. So again, all of these I was consistent with the LIAT method, but this is a general guide that works like 95% of the time. It doesn't always work. So we're going to look at an example where it falls apart. So if I was to use LIAT, then I would see, okay, there's no logarithms, there's no inverse trig functions. So I would choose an algebraic expression. And so I would have to pick x over 1 plus x squared as my algebraic expression. And if I go down that path, you'll see, first of all, if that's u, then the derivative is going to be very complicated. I have to apply the quotient rule, and it's actually not going to go anywhere. I'm not going to work all that out because it'll be a mess, but feel free to try on your own what happens if you pick u equals x over 1 plus x squared. So LIAT isn't going to work in that case. So sometimes that's going to happen, even though LIAT is a nice, useful shortcut. That's why I didn't talk about LIAT prior to this point. I instead just talked about other ways to reason through how to pick u and how to pick dv, because again, LIAT isn't always going to work. So the main reasoning we think about is I want to pick u in a way that when I take my derivative, I somehow simplify the integrals I'm working with. And so if I look at this, I think x e to the x, if I try to take the derivative of that, it's a product rule, but it's a simple product rule. It's about the simplest product rule you could ask for. And I'm going to get x e to the x plus 1 times e to the x. So I'm going to end up with, if I factor out e to the x, a 1 plus x expression. You might not see that immediately. You might have to just try it and write it down. But I see if I have a 1 plus x with my du, maybe I'll somehow be able to cancel one of these 1 plus x's in the denominator or something like that. So we're going to try that. So u equals x e to the x. So I apply my product rule. I get the derivative of x times e to the x plus x times e to the x derivative, all multiplied by dx. So this is e to the x plus x e to the x dx. And then I can factor out my e to the x and get 1 plus x dx. But that means dv, right? If u is x e to the x, dv needs to be everything else. That's the dx over 1 plus x squared. So that's not too hard of a function to find the antiderivative for, but it's enough that I'm going to write it off to the side. So instead of writing dx over 1 plus x squared, I'm going to write 1 plus x to the negative second power dx. And there would need to be a substitution here, w, but my dw is just going to be 1. So that substitution works out really nicely. I get 1 plus x to the negative first power divided by negative 1. And again, dw is dx, so when I substitute back in, it doesn't change anything. There's a plus c. And altogether, I'm dividing by a negative, so the whole thing is negative 1 over 1 plus x plus c. So we'll put that up here. V is negative 1 over 1 plus x. So again, key is sometimes LIAT, those shortcuts don't really work, and we might just have to be creative and think up a different solution to the problem. And you might have to try a couple things. You might try something that doesn't work. That's okay. It's okay to go down a path that doesn't take you anywhere, as long as you realize when it's causing you problems and try something else. Okay, so now we'll take our integral and we'll write it out. So we've got the integral of u dv is uv minus the integral of v du. So uv, that's x e to the x times negative 1 over 1 plus x minus the integral of v du. It's negative 1 over 1 plus x times du, which is e to the x times 1 plus x dx. So what happens? Well, the 1 plus x cancels with the 1 plus x in this numerator. What else happens? Let's see, we've got a negative 1 here, so I'll put that negative in front. We get negative e to the x over 1 plus x. These two negatives cancel, so I get plus the integral, and all that's left inside is e to the x dx. So this is negative x e to the x over 1 plus x plus e to the x plus c. And now, this would be fine if a student turned in this answer, negative x e to the x over 1 plus x plus e to the x plus c. I would be totally happy with that. But this one simplifies really nicely, so I'm going to go ahead and take that extra step, and I'm going to find a common denominator so I can combine these two expressions together. So I just multiply the top and bottom by 1 plus x. That's negative x e to the x over 1 plus x plus e to the x times 1 plus x gives me e to the x plus x e to the x all over 1 plus x. Don't forget your plus c. And now, since I have a common denominator, I can add these all together and we get negative x e to the x cancels the positive x e to the x. Might be a little bit more clear if I write it all as one fraction first. So I'm going to do that. Negative x e to the x plus e to the x plus x e to the x all over 1 plus x plus c. And the negative x e to the x cancels the x e to the x. So this cleans up to just e to the x over 1 plus x plus a constant. Okay, that's it for that one. So again, this example is just to demonstrate primarily that sometimes you got to think outside the box. Even though you can use this LIAT as a general suggestion, you shouldn't be trapped by it. Try to think about these problems in other ways, like, hey, what kind of thing, if I take the derivative, makes this problem simpler to work with? Okay, moving on. And this is going to be our last example here. Prove the following reduction formula. So, of course, proving this just means rigorously showing that it's true using the tools that you already know. So we know integration by parts, and this definitely looks like it's some sort of integration by parts expression. Now, the tricky part is figuring out how to rewrite this cosine to the nth power of x dx in a way that I can apply integration by parts. And so I'm going to look at the right-hand side of this formula for a hint. So I've got, okay, if this is my integral of u dv, then this should be my product of u times v minus the integral of v du. Now, u times v here, well, this thing, sine of x, kind of looks like it could be v, because sine of x is the antiderivative for cosine, right? And so that's sort of my hint. That's how I figure out that, hey, if I just start by rewriting my integral as cosine to the n minus 1 power of x times cosine of x, I'll be able to apply integration by parts to this. And look, the antiderivative of cosine of x is sine of x. Okay, so this is a pretty tough one. We've figured out the trickiest part, but the rest of it is still a little challenging to work out. So if you need a moment to take a sip of water, now's a good point to pause. All right, here we go. I've identified that, hey, u is going to be cosine to the n minus 1 power x, and dv is going to be cosine of x dx. So v is just sine of x, the antiderivative of cosine, and du, okay, well, I've got to apply a power rule and a chain rule, right? Because when we write cosine to the n minus 1 power of x, this really means cosine of x to the n minus 1 power. So I apply the power rule, that's n minus 1 times cosine of x to the n minus 2 power, but I also have to apply the chain rule and take the derivative of cosine, which is negative sine of x dx. Didn't give myself much room there. So now we apply our integration by parts formula, and we get uv, that's cosine to the n minus 1 power of x, times sine of x, minus the integral of v du, that's sine of x, times n minus 1, times cosine of x to the n minus 2 power, times negative sine of x dx. So there's kind of a lot to clean up here. We do see some things that make sense. I've got an n minus 1 expression here and n minus 1 expression up here, but the rest of this doesn't look quite right. So we're going to do a little bit of rewriting and see how we can simplify this expression a bit. Okay, rewrite that first part. Didn't do anything there. Now look, I've got a negative out here, and one of the terms in here is a negative. Negative times negative is a positive, so we'll just make this whole thing positive. And then on top of that, n minus 1 is a constant, so I'm going to pull that n minus 1 in front of the integral. And then inside the integral, I've got sine of x times sine of x, so I'm going to put those together as sine squared of x. And then the only thing left is my cosine of x to the n minus 2 power dx. Okay, so I look at this, I see sine squared of x times cosine of x to the n minus 2 power, and I think, okay, I've got this combination of sine and cosine. Maybe if I rewrite sine squared of x in terms of cosine, I can do something else with it. And we know that sine squared of x plus cosine squared of x is 1. That's the Pythagorean identity. And so I can always write sine squared of x as 1 minus cosine squared of x. And so that's what we're going to do. I'll replace sine squared of x with 1 minus cosine squared of x. And now I'm going to take this, I dropped an x, cosine of n minus 2 of cosine to the n minus 2 power of x. I'm going to take this cosine to the n minus 2 power of x, and I'm going to distribute it to both of these terms here. And so I get cosine to the n minus 2 power of x dx minus the integral. All right, I distribute it to the 1. I just get cosine to the n minus 2 power of x dx. I distribute it to the cosine squared. If I add 2 to n minus 2, I just get n. So this is minus the integral of cosine to the nth power of x dx. And now we've gotten to the key step. This should look very familiar to a previous situation because our integral I is the nth power of cosine of x dx. So this is I again. So now I'm going to do the same sort of thing I did before and write this as an algebraic expression. My original integral is equal to cosine to the n minus 1 power of x times sine of x plus n minus 1 times the integral of cosine to the n minus 2 power of x dx minus I. And then I'm going to solve it algebraically. So I distribute this as n minus 1 across here. And so I equals cosine to the n minus 1 power of x, sine of x, plus n minus 1 times cosine to the n minus 2 power of x dx, minus n minus 1 times I. So now I just have to add the expression involving I to the other side. And if I have n minus 1 times I plus 1 times I, that's ni. So I get n times I is cosine to the n minus 1 power of x sine of x plus n minus 1 times the integral of cosine to the n minus 2 power of x dx. And the last thing we have to do is just divide every term by n. And then we're done. I is cosine to the n minus 1 power of x sine of x over n plus n minus 1 over n times the integral cosine to the n minus 2 power of x dx. Okay, so that's definitely the toughest one of this set of problems. And I would say that's really about as hard as it gets. But this kind of process leads to what we call power reduction formulas for cosine, and a similar process can be done for sine to any nth power. And this can be useful when you need to integrate things like sine to the 10th power or cosine to the 16th power or something like that. It can simplify the process. Okay. That's it on this one. Thank you for watching.